I have to say I'm super grateful to Simon's Foundation for the support because, as we all know, these are tough times in terms of federal funding. This is the group that we have at Johns Hopkins. There are several students and postdocs. I have highlighted in blue the ones that are graduating this year and on the job market, because I know that there are some colleagues here who could be possible employers. Jay Wadekar is about to move on to UT Austin to start a faculty position. And anyway, much of the things I will say are actually thanks to the work of all of these brilliant people that you see over here. I decided I had to say I'm in a very good position because we are almost exactly on the 10th anniversary since the first detection of gravitational waves. And I know that this is a very broad audience, so I decided to start off with a little bit of a soft introduction to what gravitational waves are and why we've been so excited for the past 10 years and what we have learned from this new field of astronomy that just opened up. And then I'll discuss briefly what we are learning as we go from measuring individual gravitational wave events to measuring a whole population. And at the end, I'll talk about something that is very near and dear to me, which is the idea of using gravitational wave astronomy to test the nature of black holes through something that we call black hole spectroscopy. So one of the best days of my life was about 10 years ago, when on January 20, I got an email from the editors at the American Physical Society saying that they were about to receive a pretty important paper related to the possible observation of gravitational waves. And they asked me whether I wanted to write the viewpoint to accompany that article. And I guess I said yes. And I couldn't sleep that night waiting for the article to come. And in the article that I wrote to accompany the discovery paper, I tried to explain why this was such a major achievement and what the basic ideas behind the detection were. And the key idea for those of you who don't work in this field is that gravitational waves act as tidal forces. So the way that they distort a ring of particles is the one that you see here in this animation. They are basically analogous to tidal gravity, the way that gravity pushes and pulls on the oceans, on the Earth. As you can see in this illustration, was taken from a beautiful book by Kip Thorne. The problem is that the amplitude of these gravitational waves is ridiculously small. The first calculation of this amplitude was done by Einstein himself, just 1 year after the formulation of the field equations of general relativity through what is called the quadrupole formula. The quadrupole formula tells you that the relative variation in that circle that you see over there is typically of the order of magnitude of the second time derivative of the quadrupole moment of the system divided by the distance to the system. So if you imagine a gravitational wave generator on Earth, you take two masses of about a ton and you spin them around as fast as you can, and you require the minimum distance so that you can apply the formalism, so you had to be in the wave zone, meaning that the distance from the source to the observer has to be larger than the wavelength. Then you realize immediately that this number has to be so ridiculously small that Einstein himself stopped thinking about this kind of stuff, right? And detection seemed just so far off that the only interest of gravitational waves for about 50 years or so was purely theoretical and related to topics in quantization of gravity. However, there are sources out there in the universe, for example, solar mass black holes or supermassive black holes that can be so massive and move so fast that that number, instead of being 10 to the minus 39, becomes something of the order of 10 to the minus 21, which is still crazy, but over 100 years later, the technology has caught up, and now we have finally been able to detect these oscillations. The key idea is due to Ray Weiss that you see over here, who got the Nobel Prize for it and recently passed away. He's a giant in our field. And the idea is to build a gigantic interferometer. The LIGO interferometers are basically two enormous vacuum tubes, and you shine a laser, and then what you're looking for are changes in the interference pattern generated after these lasers bounce off two mirrors that are located at the end of the pipes. So through lots of technological developments that I don't have time to discuss, and a lot of experimental effort supported by the National Science Foundation over a very long period of time, we finally managed to construct a detector that is sensitive enough. This is one of the two that we have here in the US, the one in Livingston, Louisiana. There is another one in Hanford in Washington State. There's also a third detector in my home country of Italy in Cascina, which, funnily enough, I never visited, while I've been to the LIGO detectors many, many times. And what happened since then is that we had several observing runs. So there were, so far, 4 observing runs that go under the name of O1, O2, O3, and O4. We just got a data release from what is called O4A, the first stretch of the 4th observing run. And what you see at the top of this slide, the slide itself is taken from a special issue of Astrophysical Journal dedicated to the O4A catalog, is the number of detections in each of these observing runs. So the first observing run, the one that gave us the first detection, also gave us a total of 3 events. And then the number of events went up to 8, and 39, and 35, and now 128. And why was that possible? It was possible because these detectors have been improving dramatically over time. What you see here from the same introduction to the O4 catalog is what is called the strain sensitivity of the detectors. Basically, the lower this curve, the better. It means that you can see farther out in the universe. And you also see here the duty cycles have been getting better and better. Bottom line is that now, if we observe the same events that we started observing about a decade ago, we're going to see it much louder and clearer than we could 1 decade ago. And most of the events that we have observed so far consist of the spiral merger and ring down of binary black holes. So the idea here is that you start off with 2 black holes that are very widely separated, and they emit gravitational waves. As they emit gravitational waves, the system loses energy, and the 2 members of the binary get closer and closer together in what is called an in-spiral, until eventually they merge together. So the initial phases of this in-spiral can be described using something called post-Newtonian theory, which is basically an expansion of the Einstein equations in powers of v over c, where v is the orbital velocity of the binary. When these 2 objects are very close, you need numerical relativity to solve the Einstein field equations. And then after the 2 objects have merged, they, according to general relativity, relax to a rotating black hole solution, what is called a Kerr solution. And that part of the signal can be computed using something called black hole perturbation theory that we'll describe later on. So the signal that I was showing in the slide before is basically a picture-perfect replica of what numerical relativity has allowed us to compute over the past 20 years or so. And what you see here is that the exact same signal was observed both in the LIGO-Hanford and the LIGO-Livingston detectors. The signal is separated by some amount of time that you can use to do triangulation and locate the source in the sky. And what you see at the bottom here, those are called time frequency diagrams, and they show you that the typical frequency of the signal grows in time. The coloring on that time frequency plot at the bottom represents effectively the signal-to-noise ratio. Now, look at the scale of this plot and look at what we saw just a few months ago. This is basically a twin of the very first signal. The first signal was called GW150914, and you see that the scale down there goes from 0 to about 8. And what you see here is that the new signals, you can hardly see the noise superposed to those signals in the data because they were so loud. This particular signal that I'm showing you here has a signal-to-noise ratio of 80. It's by far the loudest that we have seen so far, and it allows us to do spectacular tests of general relativity, as I will describe later on. Now, there is a whole network of gravitational wave observatories. Besides the LIGO detectors and the Virgo detector that I described before, there is also a detector in Japan called KAGRA. And there's a plan to construct a LIGO-like detector called LIGO India in India. Besides, the National Science Foundation has already approved what is called A+. It's a plan for upgrades within the existing LIGO facilities. And hopefully there will also be another round of upgrades that goes under the name of A-sharp. But this is only the beginning, because what we really want to do is open up the gravitational wave frequency band in all possible frequencies at which we expect there to be astrophysical sources that produce gravitational waves. So we know, for example, that there could be imprints of gravitational waves in the CMB, and people have been actively looking for those. The pulsar timing arrays very recently have announced evidence, I should say, for the existence of a stochastic gravitational wave background that is presumably produced by mergers of massive black holes throughout the universe. And besides planned upgrades of terrestrial interferometers, there is also more than the idea now, an actual project that was approved in Europe to launch a space-based gravitational wave detector called LISA. In fact, we are almost exactly on the 10th anniversary of the launch of LISA Pathfinder, a technology demonstration that proved that the technology necessary to achieve those measurements in space is actually feasible. And LISA, the mission that was demonstrated through the Pathfinder about 10 years ago, has been adopted by the European Space Agency at the beginning of 2024 with a scheduled launch of 2035. And many of my colleagues are working on this, me included, actually. So besides that, there are many exciting new ideas to detect gravitational waves. In Europe, there is a big plan to develop a next-generation observatory called the Einstein Telescope. The original plan was to have a single site with a triangular detector similar to LISA, and possibly underground and cryogenic, which is very difficult to do. Now people in Europe are reconsidering the possibility of having two L-shaped detectors similar to the two LIGOs. And besides this, there's a similar plan in the US to construct a 40-kilometer follow-up to the LIGO facilities that will be called Cosmic Explorer. Vicky Calogera here was chairing the NSF Mathematical and Physical Sciences Advisory Committee that evaluated the possibility of constructing one or two of these detectors. And besides that, there are also other ideas that are maybe not quite as well-grounded as these, but there are ideas to construct gravitational wave detectors on the moon, or even to use the moon itself as a giant resonant bar to observe gravitational waves. And there are ideas based on atom interferometry, and even ideas to follow up on LISA in Europe. In fact, I'm part of a working group that is deciding what to do as a possible follow-up to LISA. We recently had a workshop at Johns Hopkins on this idea of using the moon itself as a gravitational wave detector, and it's very exciting, but I don't have the time to tell you what happens. But the key idea is that Joe Weber himself, who had constructed the first resonant bars, had already deployed seismometers on the moon. And what you want to do is use the moon itself as a big resonant bar to detect gravitational waves in the decihertz band. A more futuristic plan is to deploy a LIGO-like facility on one of the moon craters, but that is probably going to take more time. So this plot over here summarizes everything that I said so far. It's all very exciting, but we're only at the beginning. And where we are now is more or less at the stage of advanced LIGO over there. We want to increase the sensitivity of our detectors by about a factor of 10 on Earth. We are already building LISA in space to observe gravitational waves at lower frequencies from more massive objects. And there are all these ideas to open up the gravitational wave spectrum in other bands. Now, the second part of my talk, what have we learned from these 10 years of gravitational wave astronomy? I would argue that we have learned a lot. First of all, what you see here is a time frequency representation of the signal, similar to the one that I've shown you before, but now for all of the events that were observed in what is called the first gravitational wave transient catalog. And you see that most of these signals look alike. One of them doesn't quite look alike, and it's the one at the bottom right, if you have good eyes. That is not a binary black hole, that's a binary neutron star. And unlike binary black holes that only last for a fraction of a second or maybe a few seconds in the frequency band of the detectors, this signal lasted for something of the order of minutes. That's because the masses of the inspiraling objects are much lower. And the signal, you probably heard about it before because it was the first signal to be observed both in gravitational waves and in the electromagnetic spectrum. It opened up a whole new field of astronomy that goes under the name of multi-messenger astronomy. But what we have now is much, much more. This diagram is so large that you can hardly see the individual signals. And it represents all of the detections that the LIGO collaboration has published so far. There's hundreds of them, and they tell us a lot of information. Now, what do they tell us? Each of these signals says a lot in and by itself, because from the shape of those gravitational waveforms that I've shown you, you can do what is called match filtering. We produce models of the signals that depend on the parameters of the system, and by matching our models to the waveforms that we observe, we can measure parameters of the binaries. Now, the parameter that is best measured is what is called the chirp mass. It's a combination of the individual masses of the two merging black holes. But we can also measure to a lesser accuracy also the total mass and the mass ratio of the system. And when the black holes in the binary spin, they cause a precession of the orbital plane that allows us to measure also what is called the effective spin parameter. It's basically a weighted sum of the individual spins of the two black holes projected along the direction of the orbital angular momentum. So think of it as mass 1 spin 1 plus m2 spin 2 divided by the total mass. And there is another combination of the spins that tell you how strongly the signal is precessing that is called chi-p for precession. We would also like to measure eccentricity. Unfortunately, it's typically very hard because the theory of gravitational radiation tells us that the effect of gravitational waves is to circularize the binaries. So by the time they get into the LIGO frequency band, most of them are almost exactly circular. And we can also measure the remnant mass and the spin of the black hole produced as a result of the merger and the sky location of these signals. Now, this can give you a lot of information. And one of the key ideas is what I show in this cartoon that is taken from a paper that I wrote with my former student, Davide Gerosa, now almost 10 years ago. The idea is that we expect many of these events to be produced through isolated evolution. Isolated evolution, Vicky is an expert. You basically start off with two stars. One of the two stars explodes and produces maybe a neutron star or a black hole. The other star explodes and produces a neutron star or a black hole. And then something brings these two objects together. That's something we believe is probably common envelope evolution. And by the end, you get a merger of these two compact objects. That is called isolated evolution. It basically relies on supernova physics to explode these stars and create compact objects. However, it's also possible that these objects have already been created by collapse, and there's dynamical phenomena that can bring individual compact objects together and produce repeated mergers. So this produces different signals because general relativity tells you that if you take two black holes and you merge them together, you typically produce a remnant that spins at about 0.7 times the maximum rate allowed by general relativity. So, for example, you would expect that if you have repeated mergers, you will have mass ratios that are closer to 2 to 1. Say that you start with all black holes having 10 solar masses. Then after a first round of mergers, you're going to have 20 plus 10. And then you're going to have 30 plus 10 or whatever, or 20 plus 20, and so on. And the spins of black holes that are produced by repeated mergers should typically be higher than the original spins, assuming that the original spins were low. Also, if your black holes are produced dynamically, you would expect the spins to be randomly distributed because dynamical processes don't care about alignment, while isolated evolution presumably would produce spins that tend to be more aligned with the orbital angular momentum. These are all things that you can check by measuring the parameters of individual events. I'll give you an example. This is from one of the early catalogs, so you don't have 100 events, right? And it shows you the diversity of signals that we have observed. You will notice that in this plane, which is the mass ratio versus total mass plane, many of the signals look like bananas. That's because the parameter that you measure better is this chirp mass, which is constant along one of those bananas. However, you can determine more or less well both masses of the system. Once you know the total mass and the mass ratio, you can determine both masses. You will see here that signals belong to very different classes, okay? So I want to give you a very short summary. I'll spend a few minutes on this slide of highlights from what we have learned from the first 4 observing runs. Of course, the first event was the most spectacular because it told us that gravitational waves exist and they are detectable, and they were produced by 30 solar mass black holes, which up to that point we weren't even sure that they would exist. Then there was a second event called the Boxing Day event because it happened the day after Christmas that was much longer, and because it was much longer, it allowed us to observe some effects due to the spin. It was the first measurement of a non-zero spin in one of the black holes. And presumably it also produced a remnant kick. This is something else that I didn't tell you. When 2 black holes merge, the conservation of momentum, they radiate gravitational waves in a preferential direction, and the binary recoils in the opposite direction by conservation of momentum. So this is probably the first signal in which we could measure a non-zero kick. Then there was the binary neutron star that I already told you about that taught us a lot of things about the connection between gamma ray bursts and binary neutron star mergers, kilonovae, and so on. And then there was another event called 1904-12 that was very asymmetric. Because this event was very asymmetric, we believe that there have to be multiple formation channels at play. And one of the questions is whether if these very unequal mass black holes are formed dynamically, the fact that the system has a 3-to-1 mass ratio is suggestive that it might have been created by repeated mergers, as I explained before. Well, the question is, because these black holes recoil, the environment in which these multiple mergers are produced has to be able to retain the black holes in there so that they can merge more than once. So this tells you something about the environment in which the black holes merge. For example, globular clusters are not massive and compact enough to retain binaries so that they merge many times, but nuclear star clusters are, and maybe AGNs are. So people started thinking more and more about nuclear star clusters and AGNs as possible nurseries of black hole mergers. Then we had a second binary neutron star merger where we can only say, because we haven't seen an electromagnetic counterpart, that the merger progenitors are consistent with a binary neutron star. But this event itself was also quite surprising because the masses of the neutron stars are higher than the typical masses of neutron stars that we observe in the galactic population of neutron stars. And then there was another spectacular event, 1905-21, that demonstrated that intermediate mass black holes exist. So we know that there are stellar mass black holes. We know that there are supermassive black holes at the centers of galaxies. Our own galaxy has one of about 10 to the 6 solar masses. But how do black holes grow from being 10 or 30 solar masses all the way to 10 to the 6? There have to be additional intermediate mass black holes in there. And this event was the first proof that they actually exist because it was the merger of 2 black holes, one of which was located within the so-called upper mass gap, and the remnant had a mass of about 140 solar masses. I didn't tell you about the upper mass gap, my bad. So the idea is that when you have core collapse supernova, my colleagues who do supernova simulations tell me that it's very unlikely to produce black holes with masses between 60 and 130 solar masses. And the reason is that if your initial star is too massive, during the collapse you can have, through electron-positron conversion into photons, a depletion of the pressure that causes an explosion, and eventually you don't create black holes at all. It's called a peri-instability supernova. So what we saw here is that there are black holes in the region that should be forbidden. And maybe they ended up there through repeated mergers. We don't know. There's a lot of work in astrophysics theory to explain these objects. Another oddity is this 1908-14. It's an event where the primary is very, very massive and the secondary is very light. In fact, it's either the heaviest black hole that we have ever seen or the lightest the heaviest neutron star or the lightest black hole that we have ever seen. Then we saw 2 mergers of neutron star black holes. That was also completely not obvious that these objects exist in the universe and merge. And then we saw an event where people argued that we have observed clear signatures of orbital precession, and other people argued that maybe it was just a problem with the data. And this event brought up a bunch of problems, because when we did our tests of general relativity, it produced apparent violations. But we don't believe that general relativity was violated in this event. We believe that the issue is either with our models of the waveforms or the quality of the data. And then, from the latest catalog, 3 of the highlights include one event that populated the so-called lower mass gap. No one really believed, I think, that this lower mass gap actually existed, but you know, there was some, let's say that electromagnetic observations tend to suggest the existence of a gap because of the way we identify black holes in electromagnetic observations. We say everything that is very massive and we cannot explain is a black hole. So people were arguing for a long time whether there would be black holes in the range between 3 solar masses and about 5 solar masses, and now we have an answer. And then there's 2 more events that I want to highlight, and then I'll stop with this catalog. One is the merger of 2 intermediate mass black holes, which was absolutely stunning in many ways. It's also an event that is very difficult to explain because the primary of this binary seems to be spinning very fast, even faster than what you would predict by repeated mergers. And the last event will be the subject of the second half of my talk, so I will not talk about it very much, and I'll move on. Now, I hope I convinced you that all of these events have taught us a lot. And what we want to do next is improve the sensitivity of detectors on Earth, go from LIGO to what is called sometimes Voyager, or sometimes A+, which is the best facility that you can, the best technology that you can deploy within the current LIGO facilities. But then, if we're actually going to be able to construct Einstein Telescope and Cosmic Explorer, we're really going to enter a new and completely different era. As you can see here, with the sensitivity of the advanced detectors, because those are going to be about 10 times more sensitive, and because the gravitational waves probe the amplitude and not the energy of a signal, an increase by a factor of 10 in the luminosity distance that you can observe means a decrease of the cube of, an increase by the cube of that in the volume that you probe. So if you increase your luminosity distance horizon by a factor of 10, you increase the number of events that you can see by a factor of 1,000. Now we're observing about 1 or 2 events per week, and we're going to get to the regime where we are going to see hundreds of signals per day, which poses all sorts of problems in terms of data analysis, as you can imagine. And however, there are also new opportunities because you're going to have much longer waveforms, you can do better sky localization, you can see many more counterparts, and so on and so forth. I think this animation is cute, and I want to show it to you because it gives you a very clear visual idea of where we are now with O3, O4, and where we're going to be in terms of the number of detections as we move forward if things go as planned. And you can see that we're going from observing a few hundreds of events, that's where we are now with O4, to observing all the binaries that are merging in the whole observable universe. Okay, that's pretty mind-boggling. All right, so what have we learned about the population? I will focus on some of the key things that I think we have learned, and I will explain why I find them exciting. And I'll focus on these 4 areas. I told you we observe masses, we observe spins. Once we observe a lot of masses and spins, we can look for correlations between the different parameters, and then we can go after eccentricity. And at some point, when we observe too many binaries, we start getting worried because some of us actually want to do cosmology with gravitational waves. We want to observe gravitational waves that were produced by the Big Bang. And if we have too many astrophysical sources, it's too much of a good thing because you want to subtract those sources to look for cosmological backgrounds. So masses. This is a plot that, if you work on gravitational waves, is pretty famous by now. It's a plot of the mass spectrum of the primary in these binary black hole progenitors. And just by taking a look at this plot, you can tell that overall the shape of the distribution that you inferred depends on some details of the data analysis that I will not go into. But it's pretty clear that there is a very sharp peak at around 10 solar masses.
What is the vertical direction?
It's just the y-axis, is that what you're asking about? It's just an overall normalization that you don't particularly care about this. Think of it as a probability distribution of it's the rate per unit mass, okay? So you take all of the events that you observe in the local universe and you distribute the rate and you measure the rate per unit mass of the primary, okay? So you see that that rate is sharply peaked around 10 solar masses. There is a second peak that is pretty visible around 35 solar masses. Now we would like that peak to be around 45 because core collapse supernova tells you cannot produce black holes at masses larger than about 45. There are some uncertainties, but pushing the peak down from 45 to 35 seems a little iffy. So we think that that peak could be related to the fact that there is a channel that is isolated evolution and a channel that is hierarchical, but this is not completely clear. And you can also see that there is some evidence in the fourth catalog, but not in the third catalog, marginal, for yet another peak at 20, which is cute, because then you can say that you start off with 10, and then you had 10 plus 10 that gives you 20, and then you had 20 plus 10 that gives you 30, and you know, this mass distribution starts making a lot of sense. However, there are many things that honestly we don't understand and we want to understand. For example, you can contaminate the no man's land that is predicted by per-instability supernova theory. Spins. When we measure the spins, and some collaborators of mine have worked a lot on spin precession. We were hoping to see a lot of very fast precessing binaries. However, the LIGO distribution is compatible with many of the spins being very close to 0, or maybe 0.2. Now, that's disappointing for me, but maybe it's related to the way that stars collapse and form black holes. There is something that carries away the angular momentum, and you're left with black holes that are typically kind of slowly spinning. However, there is the possibility that because masses are easier to measure, the distribution of spins is skewed towards low values just because our measurements are not sensitive enough. And in fact, as we measure more and more binaries, there's the possibility that this distribution will get farther and farther away from 0. And also, there is some evidence now in the new catalog for some asymmetry in the tilt distribution of the spins. This suggests that maybe part of the population is preferentially aligned and part of the population is not. And so, once again, it lends credence to the idea that multiple formation channels are at play. Another thing that you can do when you start having hundreds of events is to look for correlations. So what you see here is a plot. Look at the black crosses first. That shows you the correlation between the mass ratio and the effective spin. If you forgot, the effective spin is m1 spin 1 plus m2 spin 2. And we didn't expect to see this correlation. In fact, we can't really explain it. And one of the ideas that we tried out with a student, Santini, that you see down there, is perhaps this correlation happens because when you have hierarchical mergers, they don't happen in a spherically symmetric environment in which the spin directions are completely random, but they happen in an environment like KGNs, where maybe because of alignment of the individual spins with the accretion disk around your massive black hole, these spins are aligned to begin with, and then you can form black hole spins that are more aligned, and so this effective spin is going to be large when you have many multiple mergers. And this seems to go in the right direction. However, I cannot honestly argue that it completely explains the data, and in fact, in the newest catalog, this correlation seems to be going away. So the crosses are the data. And the circles are what we get from this simple model in which we take black holes and we make them merge in a spherically symmetric environment or in an environment in which you have preferential axial symmetry, for example, an AGN disk. And so axial symmetry seems to be more compatible with the data than spherical symmetry, but we don't know for sure. It's just one of the things that you can start exploring when you have correlations between parameters. Another correlation that is emerging is between total mass of the systems and spin. So there are recent papers that argue that the low mass systems have spins closer to 0 than the high mass systems, which once again seems to make sense with the general picture that I've given you. And other correlations that we're exploring is, our detectors become more sensitive? We really want to understand if there's some cosmological evolutions in the properties of the mergers. So people have been looking at things like correlations between mass and redshift, or spins and redshift, and so on. One last thing that I want to point out is that I didn't talk about eccentricity very much, because most of the binaries that we see are almost completely circular. However, Katie Breivik and Vicky some years ago, and also Alberto Cesana, Tsushi Nishizawa, and I started thinking about a possibility, which is the following. The reason we don't see eccentric binaries is that a very simple calculation based on the quadrupole formula tells you that the eccentricity of the binaries scales roughly with the inverse of the frequency. So by the time these binaries have become very close, which is what we see with LIGO, their eccentricity has reduced to pretty much 0. However, if you were able to observe the same binaries at lower frequencies, it's possible that many of them would be much more eccentric. In fact, what you see here on the left is the result of simulations by one of my students, Kostas Kritos, who simulated clusters and how binaries would be formed in different possible sub-channels within clusters. And you can see that at different values of the orbital frequency of the binary, you can see very different distributions of the eccentricity. So one of the reasons why I got interested in these Desihertz detectors on the moon or beyond is that if you had a detector that is sensitive in the Desihertz, you could be much better at probing information channels of binaries. And that's all I want to say. I'm going to move to the last part of my talk. So the last part of my talk is what I used to do when I started off. I've always been interested in gravitational waves because I was naive enough that I thought that one day they could be published, but I started off as a theoretical physicist. And what I will discuss now is how we can use gravitational waves to test whether these things that we see, that I try to convince you are black holes, really are black holes as they are predicted by general relativity. Now, I will go back to the very beginning. The very beginning is 1 year after the discovery of the field equations by Einstein and Hilbert. Karl Schwarzschild famously was on the Russian front, and he tried to find a spherically symmetric solution of the Einstein field equations purely analytically, and remarkably, he succeeded. And he sent the solution to Einstein, who said, wow, I didn't expect this to be possible at all because the equations are horrible, but you managed to do it. And the solution, however, initially was thought to be a mathematical curiosity because clearly, when you look at the Schwarzschild metric up there, it has a singularity at r equals 0. It seems to have a singularity at r equal to m. Now we understand that the singularity at r equal to m is actually a coordinate singularity. You probably know this story. I'm not going to go into it too much, but the key questions after the discovery of the solutions were, number one, is this physical? Can it be produced through gravitational collapse? Now, there was a famous paper by Oppenheimer and Snyder in 1939 that said, yes, if you assume spherical symmetry and that all matter is made of dust. Now, I don't think any astrophysicist would believe you if you came up with such a proof. And in fact, many Russian mathematicians said, no, that's not a general proof. And if you take general conditions for the collapse, you can prove that the collapse to a singularity is chaotic. They came up with this beautiful BKL theory and so on and so forth. So there was a lot of arguing. John Wheeler, that you see pictured here in front of one of his famous blackboards, got interested in this problem after World War II and decided to investigate the question whether nuclear physics can halt the collapse. And you know the end of this story because Roger Penrose won a Nobel Prize. There are general theorems that prove that even in the absence of spherical symmetry, the general outcome of gravitational collapse is going to be a black hole, either of the Schwarzschild or Kerr nature within classical general relativity. Now, the second question is, okay, Roger Penrose solved the problem of whether we can form them. Are they stable? Because if they are not stable, once again, my astrophysicist friends wouldn't care. And so there was a lot of work that started off in the 1960s, actually in the late 1950s, to study perturbations of black holes and understand whether they are stable or not. So on the experimental side, the early 60s were the time where we first observed a supermassive black hole, because Martin Schmidt observed the first quasar and understood that it had to be powered gravitationally, and therefore people started thinking about black holes as the possible energy source for these objects. And Giacconi, who later came to Johns Hopkins, or actually was already there, I believe, at the time. Anyway, he proposed orbital satellites to study X-ray sources and discover Cygnus X1, the first stellar mass black hole. At the same time, Kip Thorne, who had started as a young faculty at Caltech, put together a brilliant group of students. It's still amazing if you go there and you look at the thesis of the first people who worked with him. One of them was Sol Teokovsky, who developed the formalism to study perturbations of rotating black holes. So this field has evolved enormously. We just finished putting together a 300-page review, I kid you not, on where we stand now. And we went all the way from the theoretical studies that were first carried out by Vishweshwara in 1970 to the study of black hole spectroscopy as an experimental science. And I'll try to give you a very quick run through the history of this field and why I find it so exciting now. The guy that you see here, by the way, is Vishu, who also died not too long ago, I think 3 years ago or so. You may know his daughter, Smita, who is very active within the condensed matter community. In fact, she was, I think, the chair of the division of condensed matter for the APS. And she wrote a book about her interactions with her dad, but I digress. Okay, so what was the problem that Vishu was given? Vishu was a student of Charlie Misner at the University of Maryland. You may know Misner from Misner, Thorne, and Wheeler, the big black book on gravitation. And the problem that Misner gave to Vishu was, why don't you solve the problem of two black holes coming together and merging and producing gravitational waves? And Vishu said, if I had been able to do this, I would have been the oldest graduating student in the history of humankind. So he didn't quite solve that problem, but he solved a simpler problem. And he said, okay, I cannot quite do this, but he scattered Gaussian wave packets of a black hole. So he took a single Schwarzschild black hole, and he superposed a small wave packet, say of a scalar field or a gravitational field, whatever, and he observed the signal that you emit at infinity when this Gaussian wave packet scatters off the black hole. And what he observed was a very universal signal that looks like the one that you see on the right. Actually, these days we usually plot it, imagine a reflection symmetry across the x-axis. But what you see is that initially the amplitude of the signal grows, going from the right to the left, and then the signal decays exponentially. It's a damped sinusoid. And this damped sinusoid didn't depend on the details of the Gaussian that you put on top of the black hole. Now we call it the ringdown, because what is happening is effectively similar to what would happen if you took a bell and hit it with a hammer. You hear the ringing of the bell, and the sound at which the bell rings depends on the properties of the bell and not on the initial data, on the features of the hammer that you hit it with or how strong you hit it. Now, this was understood through a series of papers. I don't have the time to summarize them all, but some of the key generalizations were due to Bill Press, who understood that basically you can understand these modes as perturbations of waves at the light ring. Okay, I will tell you a little more about this in a minute. And then it was understood that these modes could be excited in astrophysical processes. The first OE model that was studied was in this paper by Davis, Ruffini, Press, and Price. These plots are taken from that paper, where they did the following thought experiment. They took a particle and dropped the particle radially into a black hole, and they asked, what are the gravitational waves emitted by this process? Now, the energy spectrum of gravitational waves as a function of frequency, if you go to the frequency domain, looks like so. Initially, you don't emit very much at all, and then there is a peak in the radiation, and then the radiation drops like a stone. The frequency at which the radiation drops like a stone is the frequency of the oscillation mode of the black hole, for reasons that I will explain in a minute. Be patient. Okay. Then Teokovsky generalized the formalism to rotating black holes, And several people tried to understand if these oscillation modes of the black hole could be excited in gravitational collapse. At the beginning, they were doing this in perturbation theory. And the waveforms that you see here are from some of the earliest simulations of collapse to a black hole within perturbation theory. What you see is that the signal itself looks like a damped sinusoid, but more interestingly, if you fit the signal at the top by a single damped sinusoid and you subtract, the signal that is left off also looks like a damped sinusoid. Now, that is called the first overtone. And it's a hint that in your signal, you will see a superposition of damped sinusoids, okay? The first person to compute all of the oscillation modes of a rotating black hole was Steve Detweiler, who was a collaborator of Chandrasekhar, just like my PhD advisor, Valeria Ferrari, and they both worked on black hole perturbation theory and stellar perturbation theory with Chandra. And Steve, when he completed the first calculation of the spectrum of rotating black holes, said, that's how he closes the paper, actually. This is 1979, I was in kindergarten. He says, after the advent of gravitational wave astronomy, the observation of the black hole's resonant frequencies might finally provide direct evidence of black holes with the same certainty as, say, the 21-centimeter line identifies interstellar hydrogen. And that's why we call this black hole spectroscopy. The idea has been around since before I was born, okay? Now, how does this work? Let me give you a little more mathematical detail about what these quasi-normal modes are. Now, the idea is that if you consider perturbations of a black hole induced by, say, a scalar field or an electromagnetic field or a gravitational field, it doesn't quite matter, you can apply the same techniques that you use in quantum mechanics. So you use a set of angular basis functions. In quantum mechanics, you use the spherical harmonics. Here, you're going to use something called tensor spherical harmonics to separate out the angular part. Then you do a Fourier analysis in time so that all of your time dependence is absorbed into something of the form e to the I omega t. And surprisingly, after massaging the perturbed Einstein equations, which are horrible, trust me, because that's what I did as a PhD and undergraduate student. That's what I was working on. If you massage them enough, you can always cast them, this is something that still boggles my mind, in the form of a Schrödinger equation. This is pretty much always possible in general relativity. So you are left off with a one-dimensional scattering problem that involves a frequency, omega, that is related to the energy of your perturbations, and some radial potential. And inevitably, this radial potential has a very simple shape. It goes to 0 at the horizon on the left. It goes to 0 at spatial infinity on the right. And it has a local maximum that is located very close to, for a Schwarzschild black hole, R equal 3m. For those of you who have taken GR, R equal 3m is the location of the light ring. So if you take massless particles around a black hole, there is an unstable orbit at which, if I shoot a photon to the back of my head and I live close to a black hole, that photon will come back and show me that I've been balding, okay? This is only possible if you're close to a black hole, which I'm grateful. But, you know, it's a thing that can happen. So that light ring is unstable, which means that if I take the light ring and I perturb it slightly, some of the radiation is going to go out, and I will see it in the form of these quasi-normal modes. Physically, they correspond to the proper oscillation modes of the black hole, in the sense that they are the solution of the eigenvalue problem that you get when you impose that you only have ingoing waves at the horizon of the black hole, because it's a one-way membrane, and you only have outgoing waves at infinity, meaning that there is no stimulated emission. You're not throwing anything in, you're only looking at solutions for which stuff is coming out to you. Those are modes that are resonant, because they will be there even when you don't throw in any waves. That's the key idea, okay? So if you solve this eigenvalue problem, this is what you get. For a Schwarzschild black hole, you get, remember that I've used angular harmonics, so there's going to be modes with different values of L. Because gravitational waves are quadrupolar, I told you in my second slide, they start off with L equal 2. You don't have L equal 0 because it's just a mass perturbation. You don't have L equal 1 because in general relativity you conserve linear momentum for an isolated system. So you start off from L equal 2, and the spectrum looks like so. So the mode that has the smallest imaginary part is the one that I expect to dominate in the signal. And then I may be able to see modes with higher Ls or higher overtones. And I've shown you that they are present in some of the signals. Now, more interestingly, if your black hole is spinning, each of the modes that you see on the left is going to have something like the Zeeman splitting that you see in atomic physics, where introducing an external magnetic field or an external electric field breaks the spherical symmetry of the system. So each mode with a given value of L is now broken into a multiplet of 2L plus 1 modes with different possible values of M. Now, from numerical relativity simulations, we know that when two black holes come together, because they are like a rotating bar, the dominant mode is going to be the one with L equal M equal 2. So expectation out of all of this theory is that when I go and look at the binaries in LIGO, I should see first the fundamental mode, the one with the smallest imaginary part and longest damping time, with L equal M equal 2. And then maybe I'm going to see something else. Maybe I'm going to see the first overtone, maybe I'm going to see higher multiples. That depends on the properties of the progenitor binary. So this is what the whole spectrum looks like. I don't have time to go into the nitty-gritty details, but that's the general idea that I told you about. It turns out that this spectrum is unstable, which is mathematically very interesting, but I don't have time to tell you more about this. And it also turns out that the full waveform cannot be described by quasi-normal modes. This was understood through a series of works, going back to that paper highlighted in blue by Lever, where he studied the Green's function corresponding to the Schrödinger problem that I told you about before. And he demonstrated that in general, the signal contains three parts. One part is called the prompt response. Imagine the thought experiment that I gave you before. When you drop a stone or a particle into the black hole, there will be waves that are coming out of the particle, and you will see those as being produced at the location of the particle and radiating all the way to infinity. That's what I call the prompt response. Then, at some point, there's going to be a part of your signal that is going to be dominated by quasi-normal modes. But at the end, because your space-time is curved, the radiation that is coming out of the system is backscattered and then comes back again, and that produces what is called a gravitational-wave tail. It's a power law decay in time, okay? So all of these features we do observe in the gravitational waveforms that we compute. And in fact, after the first simulations of binary black holes, people tried to fit them by a superposition of quasi-normal modes. And what you see here is, in black, the very first simulation of a binary black hole by my friend Franz Pretorius at Princeton. And the lines that you see, the red line at the top left, is the fit with a single damped sinusoid. It's an excellent fit. Then you subtract it, and you see that the remainder is the blue curve, which you can fit again. And you can keep going, and you can try to improve the quality of this fit. And by fitting many damped sinusoids, maybe you can reproduce the waveform all the way to the peak. In fact, we know that we need more than one quasi-normal mode if we want to accurately measure the mass and the spin of the remnant. I also wrote papers about this with some students and colleagues. But then there came this claim back in 2019 by the Caltech group, where they said, well, we can repeat this exercise and fit with 7 modes. And if we fit with 7 modes within linear perturbation theory, we can reproduce the waveform all the way to the peak. Now, I disagree with this, because we know that general relativity is nonlinear, and we know that an expansion in terms of linear quasi-normal modes is only going to be good when you're close enough to the final Kerr solution. And by now, I would say that the whole community agrees that these initial papers' claims were not valid, and you really need to include nonlinear quasi-normal modes and the nonlinearities of gravity if you want to do the analysis properly. So initial claims, I will not get into the technical details of this plot, but initial claims that we had been able to observe more than one mode in the very first signal, GW150914, the one that I talked about at the beginning, those claims have gone away. Here I show a plot from the review that we wrote, where we compare several different groups that have repeated the analysis using different assumptions on the modeling of the signal, different assumptions on the data analysis, and the results are all over the place. So what we have learned out of this debate that has happened over the past 5 years, we have learned that nonlinearities in gravity are very important. And I had the time to explain this because it's Physics 101 at work within general relativity. The idea is the following. General relativity is really a nonlinear theory. But if you do perturbation theory, what you can do is write down the Tchaikovsky equation that describes perturbations of a rotating black hole at linear order. You solve at linear order, and then you write the perturbations at quadratic order. The perturbations at quadratic order will be the same differential operator applied to the second order wave function equals something that contains products of the first order wave functions. So I was asked by a colleague to teach oscillations and waves to my undergraduates. That's what you have when you have the anharmonic oscillator. You take your linear terms, you move them to the right-hand side, and you discover that the amplitude of the quadratic modes are the products of the amplitudes of the linear modes, and the frequencies of the quadratic modes are the sums and differences of the frequencies of the linear modes. Now the question was, is it true that these quadratic modes are there? And we did a very nice numerical relativity simulation to prove the point, and I'm showing you the animation while I talk. What you see here is not a simulation of the kind of binary black hole mergers that we see with LIGO. Here I'm taking two black holes and I'm colliding them head on. Why? Because I can do dimensional reduction, and the computational resources needed for a simulation like this are much lower. So what you see is the black hole. You're actually looking at the lapse if you like GR. And these two black holes come together, they eventually merge, and they radiate gravitational waves. Now, if I am doing the collision in this very simple setup, I can adjust the energy of the collision so that I boost my black holes and I make them collide close to the speed of light. So if nonlinearities are there, as I crank up the energy of the collision, I should see them, and I should be able to see that they scale as I promised that they would. So that's exactly the exercise that we did. And here's the results. What you see is that by the rules of the for summing angular momenta, you would expect that the L equal 2 modes are going to produce a quadratic mode in the L equal 4 with amplitude given by the square of the amplitude of the L equal 2 modes, and frequencies given by their sum. And that's exactly what we see. So case closed, quadratic modes are there. We also saw them in spiral simulations. In fact, the Caltech group also saw them, and we put our papers out together. And then you can do amplitude spectroscopy, if you want to call it that way. You can take many catalogs of binary black holes and fit the amplitudes of the linear and nonlinear modes. And you can do this systematically. There's a software package that my student developed, and you can produce beautiful things like this, where you take the initial mass ratio of the binary and the spins, and you plot the amplitudes of all these modes as a function of all of these parameters. And you discover a lot of remarkable relations between the modes that I don't have the time to describe. But crucially, I'm going back to the beginning of my talk, you remember this signal? This signal is at a signal-to-noise ratio of 80. Because it's so loud, if you look at the last part of this signal, you can see the ringdown by eye. In fact, the signal-to-noise ratio in the ringdown of this event is comparable to the total signal-to-noise ratio of GW15 or 914. And I don't take the credit for this. The credit goes entirely to my experimental colleagues. So now we have the same signal, but the ringdown alone is as loud as the original signal. And now we can look at that ringdown, and I am convinced myself, even though I'm a very skeptical and pessimistic person, Surjit knows, I am convinced myself that we have seen more than one mode there. Okay, so we have been able to do black hole spectroscopy. This is the end of my talk. There's a lot of modeling that has been happening, but I don't have time to describe it. Let me also tell you that we hope to see the quadratic modes with the next generation detectors. One of my students, Sophia, has been estimating how often we will see quadratic modes with ground-based detectors, and there's going to be maybe a few tens of events. It depends on astrophysical models. With LISA, things are going to be even better. I don't have time to describe these plots. I realize I'm out of time. There is a nice article in Physics Today that I wrote with Mark and Sophia that if you don't want to read the 300-page review, I would recommend, because it's only 3 pages. And these are my concluding slides. I will take some questions. I'm sorry that I ran a bit over time.